Hi everyone, I am M. Subhaprada, Assistant Professor of Mechatronics Department. Now we are going to see about the subject Discrete Time Signal Processing. So in this subject, here we are going to see about the Unit 1, that is Discrete Fourier Transform. So discrete Fourier transform. So in this first unit, we are going to see about the review of the signals and system. Then what are the concepts have been formed in frequency in discrete time signals. Then it summarizes, analysis, and then frequency domain sampling. Then we have to derive the formulas for DFT as well as FFT. Okay. So next we are going to see about the fast computation of DFT, then radix to decimation in time, then linear filtering. So these all the things we are going to see in this unit. Okay. So first thing will be the signals. What do you mean by signals? Means that is the signals will be defined as any physical quantity. It will vary from the time, space, or any other independent variables. So system means that is the physical device that will generate the output signal for a given input signal. So that is x of t will be sends the y of t as the output through the system. Okay. So here y of t gives the operation on x of t, that is y of t is equal to t of x of t. Okay. So there are two types of signals. One is the continuous time signals and another one is discrete time signals. Okay. So continuous time signals means that is it will be varied in accordance with time. So that is known as continuous time signals. So for example, we can see about see as sine wave, cosine wave, etc. as an example for continuous time signals. The next thing will be the discrete time signals. So discrete time signals means that is it will having the instance of times that can be signals are continuous in amplitude and discrete in time. So they will be denoted as x of n. Okay. So that will be like the single for one time period we will mark the continuous signals in the amplitude level. Okay. So next we are going to see about the basic elements of DSP. Okay. That is the digital signal processing system that will be contains the following elements. First thing that will be the analog signal. Second is the sample and hold circuit. Third is the analog to digital converter filter. And the fourth one will be filter. Fifth one will be the digital to analog converter. So these are the things that will be used in the basic elements of discrete signal processing. So here the analog signal is nothing but the real-time signal. So it may be having the speech, video, etc. So analog signals will be having the continuous time signal and it is given to the sample and hold circuit. So after completing the sampling process, the signals will be given to ADC blocks. So ADC will convert analog to digital signal and it will filter the blocks, then removes the unwanted noises. So the filter will be removes the unwanted noises. So after that removing the unwanted noises, the output will be processed in the channel. So then we will receive in the receiver side as a pure signal. So this is the basic elements of DSP. Next we are going to see about the concepts of frequency in analog and digital signals. So that is the continuous time and discrete time signals. Okay. So the simple harmonic oscillations is mathematically described by the following continuous time sinusoidal signal. So that is xa of t is equal to a cos of ohm t plus theta. That is minus infinity less than t less than infinity. So here where a is the amplitude of the sinusoid, ohm is the frequency in radian per seconds. That is ohm is equal to 2 pi f. Theta is phase in radian and xa of t is the analog signal representation. So in terms of f, this equation 1 will be written as xa of t is equal to a cos 2 pi f t plus theta. That is we have to substitute the ohm as 2 pi f. So x of t is equal to x of t plus t. So here t is the time period in seconds and small t is the frequency in hertz. X of t is the signals which will be represent after the time period t. So that is 0 less than or equal to f less than or equal to infinity. So we can prove that xa of t is equal to a cos ohm t plus theta. So that is a into half into e to the power of j ohm t plus theta plus e to the power of minus j ohm t plus theta. So that is e j ohm t plus theta, that is equal to cos of ohm t plus theta plus j sin ohm t plus theta. So e to the power of minus j ohm t plus theta is equal to cos ohm t plus theta minus j sin ohm t plus theta. So here we have to add the equations, that is 5th and 6th. So e to the power of j ohm t plus theta plus e to the power of minus j ohm t plus theta is equal to cos of ohm t plus theta plus j sin ohm t plus theta plus cos ohm t plus theta minus j sin ohm t plus theta. So we have to cancel, that is plus j sin ohm t plus theta and minus j sin ohm t plus theta. So the remaining will be 2 cos ohm t plus theta. So 2 cos ohm t plus theta will be written as e to the power of half into e to the power of j ohm t plus theta plus e to the power of minus j ohm t plus theta. So the result will be xa of t is equal to a by 2 e to the power of j ohm t plus theta plus a by 2 e to the power of minus j ohm t plus theta. Okay. So this is we have seen about for the continuous time signal. Next we are going to see for discrete time signal. So here the discrete time signal may be expressed as in x of n, that is a cos omega n plus theta, that is minus infinity to n less than infinity. So here n is the an integer variable. So a will be the amplitude of sinusoid. So omega is the frequency in radians per sample and theta is the phase in radians. So instead of omega we have to use the frequency variable, that is omega is equal to 2 pi f. So then the equation will becomes x of n is equal to a cos 2 pi fn plus theta, that is minus infinity to n less than n infinity. Okay, so next the properties are discrete time is periodic only if the frequency is rational number. It will having the frequencies which has been separated by the integer multiples of 2 pi and it is identical. The higher rate of oscillation in discrete time sinusoid is attained. So that is omega is equal to pi or omega is equal to minus pi. Okay, that will be equivalently called as f is equal to 1 by 2 or f is equal to minus 1 by 2. Next we are going to see about the sampling theorem. Okay, so that is any arbitrary band limited continuous time signal that can be represented in sample and recovered from the samples that has been taken at equal intervals of sampling rate, that is fs is less greater than equal to 2f, that is samples per second. So this sample theorem will be reconstruct the formulas and it will be having not possible to take the infinite number of samples. So when the analog frequency is band limited to the range given by the sampling theorem, the digital frequency will be response to the same manner. So that is f is less than 2f. So in that period the aliasing will be occur. So aliasing effect means that is the problem due to the interference of informations between the two band of frequencies. The output will be known as the aliased and it is a representation of the signals. So this effect will be avoided. How we can avoid the aliasing effect means, that is we have to due to the sampling theorem, the sampling the continuous time waveform at a high rate. So that will be avoid the aliasing effect. Next we are going to see about the Nyquist rate. So that is the sampling rate is generally referred as Nyquist rate. The proof is, consider x of t as the input to continuous signal, that is it has a finite energy and finite durations. So that is the Ts is equal to 1 by Fs is equal to sampling period. So Fs is sampling frequency. So here we are going to find the impulse function as x del of t is equal to summation k equal to minus infinity infinity del of t minus nts. Okay, so it will be represented as x del of t. So that is summation n equal to minus infinity infinity del of t minus nts into x of nts. So the Fourier transform of equation which is given as x del of t is equal to fs and summation n equal to minus infinity to infinity x of f minus nfs. So it will be written as fs into x of f minus 0 fs plus fs integral, summation n is equal to minus infinity to infinity x of f minus n fs. So the last finalist, we will get the x del of f is equal to fs x of f plus fs summation n equal to minus infinity to infinity x of f minus n fs. So we have to find out the Fourier transform for x of t. So first we have to take the Fourier transform of continuous signal, that is x of t. So that will be comes as x of f is equal to integral minus infinity to infinity and x of t, that is e to the power of minus j 2 pi ft into dt. So here we have to put t is equal to nts. So then it will be denoted in the discrete signal as x del of t is equal to summation n equal to minus infinity to infinity x of nts e to the power of minus j 2 pi nts. So this we have to rearrange the equation 5. So that will becomes as x of f is equal to 1 by fs x del of f minus summation n equal to minus infinity to infinity x of f minus nfs. So it will be written as x of f is equal to 1 by fs x del of f. So if the frequency lies between minus f to f, so we have to put the equation 7 in equation 9. So x of f is equal to 1 by fs, that is summation n equal to minus infinity infinity x of n into 1 by fs, that is e to the power of minus j 2 pi f 2 pi n 1 by fs. Okay. So next thing will be we have to reconstruct the x of t. So for that we have to take the equation 10 and put fs as a 2f. So x of f is equal to 1 by 2f summation n equal to minus infinity infinity x of n by 2f to the power of minus j 2 pi into 1 by 2f. So inverse Fourier, when you have to take the inverse Fourier for above equations, we will get as x of t is equal to integral minus into infinity 1 by 2f summation n equal to minus infinity infinity x of n minus n by 2f e to the power of minus j pi by f into e to the power of j 2 pi f into df. So that is x of t is equal to summation n equal to minus infinity infinity x of n by 2f 1 by 2f integral minus infinity infinity e to the power of j 2 pi into e to the power of minus j 2 pi by 2f into df. So this will be comes in the above equation, and we have to put sin c as sin c theta is equal to sin pi by pi theta. So this will be sin c. So for that theta is sin 2 pi minus n pi divided by 2 pi minus n pi, that is sin 2ft minus n. So x of t will becomes summation n equal to minus infinity infinity x of n by 2f sin c 2ft minus n. So here is the one of the challenge, that is consider the analog signal as xa of t and 3 cos 180. We have to determine the minimum sampling required to avoid the aliasing. Then we have to find the Nyquist rate and Nyquist interval. So find the folding frequency also. So this is the problem. So here we are going to find out. First we have to write out the analog signal, that is xa of t, that is 3 cos 100 pi t. So the general equation will be x of t is equal to a cos omega t. So compare these two equations. So for a the value is 3 and for omega the value is 100 pi. Okay. So first thing will be we have to determine the minimum sampling rate required to avoid the aliasing. So that is fs is greater than or equal to 2w. So 2 pi f is equal to omega, that is equal to 100 pi. So from this we have to find out the f value, frequency value, that is 50. This is the maximum frequency. Omega is equal to 50. So the minimum sampling rate will be fs is equal to 2 omega. So that is 2 into 50, that is 100 Hz. Okay. Next question will be to find the Nyquist rate and Nyquist interval. So the Nyquist rate formula will be 2 omega. So that is 2 into 50, that is 100 Hz. Nyquist interval is 1 by 2 omega, that is 1 by 2 into 50, that is equal to 1 by 100 seconds. So find the folding frequency is third one, that is fs by 2. So sampling frequency by 2, that is 100 by 2 is equal to 50 Hz. So half of the sampling frequency is 50 Hz. So next we are going to see about the discrete time signals, that is the representation of discrete time signals, elementary of discrete time signals, classification of discrete time signals and operation of signals. Then first thing will be the representation of discrete time signals. For this we have to going to see about the explanations. So there are different types of representation of discrete time signals. The first thing will be the graphical representation, functional representation, tabular representation and sequential representation. Okay.